Okay, in this video we're going to see how we can simulate an op-amp, and the one we're going to be doing is a variation on problem 5.18 in your text. So first off, for the simulations on your homework assignment and everything, we're going to use a 741 op-amp. As we've mentioned in class, they're just what we refer to as a general purpose op-amp. They're not really great, but they're cheap, which is why we continue to use them in the labs. And so in Spice here, or in Cadence, we have this op-amp library, and if it's not installed, you can add the op-amp library. And then we'll do LM741. There are other 741 op-amps. This one's actually one that's just made by TI is all. And then I will go ahead and place that component. Now, one thing that you can see here already is that you want to pay close attention to where V plus and V minus are and where the negative and positive terminals are. When we typically look at our inverting or non-inverting op-amps, we typically have this negative being on the top. But remember, in our circuit diagrams, we drew it with the voltage being positive on the top, but when you flip it, this is actually the negative voltage supply here, and this is the positive voltage supply down here. Alright, so we're going to go ahead and add in some resistors. And the resistors got one here, one here. Now it doesn't have one here, but it's generally a good idea to put a load resistor for simulation purposes. Sometimes PSpice does not like it if you don't have a load resistor if you're going to be measuring an output voltage. Sometimes it'll be okay, but other times it's not great. So I'm going to put a 10K output resistor, and then this was 150K, and this is 25K. And then we had a ground over here, and then we're going to have a ground over here for a second. So now let's connect some of these components up. So this is connected up here. So nothing too surprising about how we're connecting these components up. This is just like we've always connected things up in the simulator. I'll move this ground over here. Alright, so I'm not done setting it up here. One thing I maybe should mention now is there's these OS1 and OS2. This stands for offset 1 and 2. We're not going to use them, and so you don't have to put anything there, but something I'd like to do, and I'll undo what I just did, is use the X button and then click these. X basically is indicating there's no connection there, and so we know that there's no connection there now. They do serve a purpose, and you can look in the data sheet to see how offset 1 and offset 2 are used. So then the other thing we had here was a 2-volt DC power supply coming in. So let's go to our source and get VDC, and then pull in another ground. And wire these up, and this is 2 volts, so I will put 2 in there. So now we can go ahead and try and run the simulation, but it won't work, and the reason being is we haven't powered up the op-amp. Now this is where we want to try and start making a little bit more sense about how to power these up. We don't necessarily want to have the negative here and the positive. We don't want to have to put another battery here. So what I find is useful is I'm going to just kind of put them over here off to the side. So what I'm going to do here is I'm going to have another 2 voltage sources, and I'll just call this one V positive, and I'm going to call this one V negative. Okay, so then I'm going to ground here, because these both need to be attached to ground as well. And this one, according to the text, this is at 16 volts, and this is at minus 16 volts. Now, you could go ahead and run a wire like okay, I'm going to run a wire here all the way up to here, maybe here. So I have now connected positive 16 volts, and then yeah, I could then go ahead and take a wire here, run it over here, and then run it down here and have negative 16 volts, and that will work. But it makes your diagram very messy, and that's actually typically not what's done with these types of simulations. Instead, what I'm going to do here is there's this little place power. Now, what I'm going to do here is I'm going to put in under place power. I like using what's called the VCC bar. So there's a VCC bar, and I'm going to put in 2 of them here. And what I'm going to do is I'm going to call this VCC plus, and I'm going to call this VCC minus. Now, what that means is anywhere I place this, now I'm going to copy and paste this. So I'm going to copy with Control-C and then paste it right over here. So what this is now saying is that, wait, this VCC voltage is at 16 volts, so this is at 16 volts. It's making this connection for us without us having to actually physically draw the wire. So right now, if I connect it up like this, I have positive VCC, which is 16 volts, sitting on the positive voltage supply here. And you can do the exact same thing with VCC minus and put it right up in here, connect it in, and now we're connected. Let me make sure I actually got that thing connected here. I don't think that connected in. There we go. So we're definitely connected in now. And now our circuit is ready to be simulated because I got my power connected up here, and I've got this nice little circuit here. Now, sometimes you might say, oh, okay, well, moving some things just so that they're not clustered together. And you can see this is much cleaner than if I had had those wires crossing all over the place. All right, so let's go ahead and simulate this. So we're going to do several types of simulations here. I'm going to call this a DC sweep, because at first what we're going to do here is, whoops, you can't have spaces in it. First thing we're going to do is just simulate it as is. But then we're going to look at something here and see and generate a graph that I think is pretty slick on some things that you can do here. Alright, so we're back here and it has simulated. Now, we could turn this voltage, DC voltage on. This isn't going to be as useful to us for much longer here. We can definitely see 2 volts, and notice that, you know, our ideal assumption that these 2 voltages are the same is somewhat accurate here. I mean, they both look like they're at 2 volts here. But this is still simulating a real op-amp as opposed to an ideal op-amp. And so you can see here we're getting 4.01 volts on the output, which really it should be exactly 14, because if we're thinking about our ideal equations, it's 150 over 25, which is 6, plus 1 because it's non-inverting, which is 7, so 7 times 2 is 14. But we're not getting 14. We're getting 14.01. And the reason for that, again, is because this is not an ideal op-amp. Alright, now the other thing, I'm turning those off here, that we want to get used to using is these voltage markers here. These are basically voltage probes. And what this will do now is it will start plotting the results for us. So I'm going to put a voltage probe there and go to this simulation thing that we have never used before. But you can then see it's just saying that, okay, over the time that it's simulated, we have just a constant voltage out, 14 volts. But we'll show you why this might be interesting by changing one thing on the simulation here. So what we're going to do here is we're going to change this. Instead of being V1, we're going to put in an, well, actually we'll do it that second. First thing we're going to do here is we're going to show the saturation regions on this op-amp and show that we really can't get to this 16 and negative 16 volts. So what I'm going to do here is I'm going to change my simulation profile. So I'm going to edit my simulation profile here. And instead of doing a time domain, I'm going to do a DC sweep. Now, when you do a DC sweep, this allows you to change the voltage of a voltage source here, a voltage supply, and it allows you to sweep it. So I'm going to sweep voltage source V1, and I'm going to do a linear sweep, and I'm going to start at negative, well, let's see here, it's a gain of 7, so negative 4, because that would give me negative 28 volts, which of course would saturate it, and we'll end at 4, and we'll do an increment of 0.1. And so we'll OK that, and then I'm going to run the simulation again here. It won't take as long to run. But now what is it doing here? Well, what did I change with respect to time? I changed the voltage source here. So it starts at negative 4 and then goes up to positive 4. So look at the x-axis, negative 4 all the way up to positive 4. And now it looks like, hey, it looks like I'm getting pretty close to the rails, but I'm not actually getting that close to them here. I mean, there is some distance here. It's not getting all the way up to 16 and not getting all the way down to negative 16. And actually, I can tell you right now that this particular model for the 741 isn't very accurate, because when we actually go into the lab, you won't even get this close to the 16 volts. I would not be surprised if you only got up to about 15 volts. So this is again where simulation, theory, and real life all come into play. Simulations are to make sure that our circuit makes sense, outputs are making sense, but then you actually have to build and test the circuit. Alright, so that's doing a DC sweep. Now the other thing I was going to show you here is why we want to maybe look at those graphs as well. And I want to put in another source, and I'm going to put in an AC source here. Actually, I'm sorry, not an AC. I'm going to do a V sine. That's a sine wave. So I'm going to put a sine wave source in here, and we're going to set the offset at 0. We're going to set the amplitude at 2 volts, and then we're going to set the frequency at 1 kilohertz. And I don't remember the purpose of this AC, but I just always set it at 1. They need that value for some reason. I'm not sure what it does. So I have the setting of the frequency here. So now we're going to run another simulation. We'll just edit this particular one. I'm going to go back to a transient. And I'm not going to change anything for a second. I'm just going to leave it as is, and then run the simulation. And you might say, look at what you're getting out. Well, it's going from 12 millivolts all the way up to 40 millivolts. Well, that doesn't even really make that much sense if you think about it, because this is supposed to be going from like negative 2 volts to 2 volts on the input, so this should be swinging between like negative 14 and 14. The key thing here is the frequency. Well, if the frequency is 1 kilohertz, 1 divided by 1000 gives me the period of 1 millisecond. So 1 period is equal to 1 millisecond. Now let's go back to my simulation profile and see how long I'm simulating for. I'm not simulating for anything close to 1 millisecond. I'm simulating for 1,000 nanoseconds. And that's 1 microsecond. So I need to change the runtime. So let's say we want to simulate, 4 or 5 periods. Well, we had changed this to maybe 4 milliseconds. And we can also set the maximum step size if we want to. And maybe I want to make so I get a nice smooth curve. I'm going to say it's 0.01 milliseconds. You can't make this arbitrarily small, because at some point you'll generate too many data points for it to plot. But that's going to be okay for us. So I don't know what happened with that, but I went back into my profile here and I just took off the S for seconds and just left it at 4M, 0.01M. I think the S was getting it confused. And so we can see here the output is a nice sine wave, and it's exactly what we were thinking. It's going up to about 14 volts and it's going down to negative 14 volts here. Now what I want to show you here, what's really cool about the simulator, what I think is, okay, so that's the output. Well, let's look at the input signal. So I'm going to put a voltage probe on the input signal. Well, now we can see this is the input signal, which is only 2 volts peak to peak. It's definitely still a sine wave, and we can see not only is it amplifying, but it's not inverting. And we can tell it's not inverting because it's going up first, going up still. And you can imagine if you simulated a non-inverting amplifier, the only thing that would happen is that this green curve would have been rotated around the x-axis. So this is maybe a little bit longer video, but we did some really interesting things with op-amp circuits.